In the previous lecture last week, we stopped here. We discussed about the aim of control in frequency response. The first one, we want to get the system stable. Please remember how can we determine stability. We want to increase phase margin, because if we increase phase margin, we can reduce overshoot. We want to increase the system bandwidth, because by increasing the system bandwidth, we can also increase the speed of the response. And finally, we want to increase the magnitude at a lower frequency, so that when we increase at level the magnitude at lower frequency, then we can have a reduced steady state error. So all this we will discuss in detail later. And I mentioned that we will have 3 controllers here, starting with gain margin, then lag compensator and compensator. Today we will look into the first one, which is the easiest one, which is known as gain margin. The gain margin is done by looking into the relationship between the baud plot and specification in time domain. Remember that we have, I mentioned to you last time, we have this, okay, phase margin versus damping ratio. If we know phase margin, we can find the damping ratio. And if we know damping ratio, we can find overshoot. So these are the relationship between phase margin and time response. So we will use that in order to design, for example, gain adjustment. The desired overshoot can be obtained by designing the phase margin. So phase margin here is very important, because phase margin determines the overshoot. Phase margin determines zeta, then also overshoot. Let's see this diagram. This is the original system. They have, this is gain margin, okay? Gain margin, not gain margin. Let's say we want phase margin, phi m. Okay, because phi m will give the overshoot that we want. But at this moment, phi m is not the phase margin, because remember, phase margin is this. Phase margin we look into when it is at 0 dB. So 0 dB is here. So phase margin is somewhere here. It's not the one that we want, not phi m. So what we'll do, we will look into the angle, the phase that we want, phi m. Then we have to make sure the magnitude here increase to be like this. If we can increase the magnitude from this to become the new one here, then we can get phase margin here, because at 0 dB we look into here, then we take the difference between phase margin here and minus 180 degrees. So that is phase margin. So it's obtained by increasing the magnitude from here to here. Okay. How can we do that? How can we increase magnitude? we can increase magnitude by, let's say this is the original system. We have K here. This is GS. Remember that when we change the value of K, when we use K, K will not affect the phase. The K is a constant phase 0. So if we change K, no different on the phase. But it will affect the magnitude. Therefore, if we increase K, it will also increase. All will increase at the same time. All increase by the same value of K. Okay. Parallel. It's all increase. And we can find how many that we want to increase by looking into this value. Similarly, we can reduce if we want. If based on the desired phase margin that we want, we can also reduce the magnitude. Reducing magnitude meaning that we reduce the value of K. This is known as gain adjustment. Why gain adjustment? Because K here is known as gain, and we adjust the gain. So this is a very simple controller. In fact, it was just called gain adjustment. The other one they call lag compensator or lag controller, but this one is called gain adjustment. Okay, let's do one example to so that you can have a clear understanding on this. For the position control system, find the value of K. We want to find K. Okay, to yield 9.5% overshoot. Okay, see this is desired. Desired 9.5%. In the transient response constant, use frequency response method. That means we want to use Bob plot. Okay, so this is one example, and in the exam will be like this. You are given a block diagram, you are given transfer function, and you will be given also Bob plot. This is the Bob plot. Okay, I took from the book. Forget this one. This one magnitude after adjustment. Just focus on this magnitude before adjustment. Okay, that is Bob plot, and remember that Bob plot must be can only be drawn by having the value of K. Without K, then we cannot draw. So first here, remember that we need to normalize to find an appropriate value of K. In the exam, once they give the Bob plot, they will give the value of K. K value to draw the Bob plot will be given. For example, here is given K equal to 3.6. Without K, we cannot draw. So that's why we have to give the value of K. So the exam will give you the value of K and will give you also the drawing, the Bob plot. Okay, so this is a part of the question, Bob plot. Okay, now we want to design K to find K so that we get 9.5% overshoot. From overshoot, we can get zeta. From zeta, we can get phase margin. When when we want to solve in frequency response, we need to know the phase margin. In the exam, these two graphs will be given. this is a graph of overshoot versus zeta. And here this is graph between phase margin and zeta. So you can use this to find the value that you want. So for example, here we want 9.5% overshoot, overshoot 9.5. About here, this is 10, so 9.5 about here, about 0.6. Okay, 0.6. Zeta 0.6. With zeta 0.6, we can see from here, from the other graph, overshoot about, phase margin about 60 degrees. Okay, maybe 59 point something. Exact actually 59.2. From the graph, we get 60. From here, 60. In order to obtain overshoot 9.5%, phase margin must be 60 degrees. Right. So that the first information that we get from the desired specification. Okay, let's see the graph here, the board plot here. Remember that desired phase margin is 60 degrees. Right? So 60 degrees mean we want something like this. This is 0 dB, 130 degrees. We want 60 degrees mean like this. Our interest is minus 120 degrees because this will give phase margin 60 degrees. And we want our magnitude like this. And if we can design so that it will be like this, then we can get 60 phase margin 60 degrees. Any question at this moment? Any question?
No, Doctor.
Okay. So now we look into the graph here, the board plot. Yes. The board plot, we look into 120 degrees. Minus 120 degrees here is here. Okay. About, this is 20. Maybe here 14 radian per second. When 120, we go up, we can see this value. At omega 14 radian per second, the magnitude is about this value, maybe 42. I just guessed this one. Maybe minus 42. Exact, if you check a book, is 44. So I use 44. It's minus 44 dB. Okay, when omega here. So currently, the phase margin is not 60 degrees. Because if 60 degrees, this point must be at 0. Then we can get this as the phase margin. So how can we make this as how can we make this to be the phase margin? We can do this by make sure all these increase by this value. All increase so that it will be like this. Okay. So that it 0 here. That means we increase all together. It can be increased, can be reduced, by increasing or reducing the value of K. How many K that we want to use is, of course, based on this 44 dB here. We can increase by 44 dB plus 44 dB. It was minus. If we add 44 dB plus, that it will be going to 0. So this is the value that we have to add. Again, the magnitude must be increased by 44 dB. In order for that point to be 0 and to have phase margin 60 degrees. So how to do? We use we know that it is log 20 log K. I use now K1. Later I show you why K1 equal to 44. You can get K1 as anti-log 44 over 20. Then we get K1 equal to, you use your calculator. It is 158 K1. Any question at this moment? Any question?
No, Doctor.
Right, we get K1. Remember that we start or we draw the dot plot with K equal to 3.6. This value of K, 3.6, is just for drawing, because without K we cannot draw. Sometimes we use K equal to 1. It may be easier, K equal to 1. But again, it will depend on the normalization that we did. Sometimes K equal to 1 will give not a proper, the scale is not good. Maybe the value is too big or too negative going at the below of the graph. So that's why we need to use an appropriate value of K to get a good range of in the graph. So it was designed initially K 3.6. We know that we need another K. We have to increase by 158. Therefore, the value of K needed to achieve overshoot 9.5% is equal to K multiplied with K1. We have to multiply both. We have to use the initial one. We have to use the one that we know must be needed to increase the magnitude. So we have to multiply 3.5 with 158. It's equal to 158 times 3.5. 3.6, sorry. 568. 3.6. 568.8. This is the value of K needed to make sure we get overshoot 9.5%. I show here also the exact value actually 59.2, the frequency 14.8, K1 162.2, and K 583.9. Why different from here? Because we estimate from here. I read from the graph. Of course, you all will get based on the accuracy of the graph and based on your reading, you will get slightly different value. The one here were taken from the book, perhaps the accurate one. This is the one that we obtained. Any question? That is called gain adjustment. But if we check back to the system, it is like this. K and GS. And now we found that K equal to 568.8. 568.8. And GS was the first GS was from here. This is GS, but we multiply all this, become GS. Here is the K, KGS. So we call the complete system, the complete transfer function. G KGS, K multiplied with GS, 568.8 divided by S plus 36, S plus 100. And also initially it was here 100. Okay, here is K, and the rest is GS, 100, S plus 36, S plus 100. I just multiply K with GS. And this is the board diagram or board plot of the complete system. How can we need to check whether we get what we want. Okay, we want 60 degrees phase margin. That means we have to check at 120 degrees, 90, maybe here 120, minus 120 degrees, about 14 just now. So we can see it is 0. 120 maybe here. This is 60 degrees, and here 0. Okay, so this is now the phase margin. Phase margin for this system is 60 degrees. Then we can get overshoot 9.5%. This is how we draw, or this is how we design gain adjustment. Okay, let's move. I want you to do this as a homework. You can plot this in MATLAB. Plot those values and then find K to yield 20% overshoot. You don't have to plot the bot plot. You can use MATLAB to plot the bot plot. And then find overshoot, zeta, and phase margin. Find desired phase margin. Then use the same procedure that we used before, earlier. Then you can get K. This is the answer. K 194200. Please try this at home so that you have a clearer understanding on this gain adjustment. If you look in detail, if you do many times, you will see that gain adjustment in frequency response is easier. It's easy. Okay? Perhaps easier than the time response. Okay, let's do one example. I just sent to you through WhatsApp in the group. Hope you managed to print this bot plot, because without bot plot, it's difficult to do this. This is a past year question, 2015-16. A closed loop system with a unity feedback. So actually it is like this. I did not plot, I did not draw the diagram. It's K, here is GS. GS, here is 40. GS is 40 SU 15S squared plus 50S. I just I directly multiply, become this. This is the system GS with K. Okay, with the gain controller K, see the question will give you the value of K, because we need to plot the bot plot. We need to have the bot plot. The bot plot for the system is given. So here is the bot plot when K equal to 1. Okay. First, find the gain margin, phase margin, and the phase and gain crossover frequency. Okay, now I want you to find phase margin and gain margin for the system based on the bot plot. Okay, do it now. Hopefully you have it. If not, look into the one that I sent to you. Find gain margin and phase margin. In 3 minutes. Should be faster. Anyone have the answer? Gain margin and phase margin. Gain margin and phase margin. Anyone? Gain margin?
Gain margin is 26
26.
and base margin is 103.5.
Phase margin.
Yes.
Let's see. Thank you, Connie. Let's see. Phase margin when 180 degrees. So this is 180 degree negative is here. This is the frequency. Okay, frequency if we check is 7 radian per second. This frequency is called phase crossover frequency. Okay, when it crosses 180 degrees, we call phase crossover frequency. Answering this is phase crossover frequency. Omega equal to 7 radian per second for this. Right, so 7, we look into here 7. 1, 2, 3, 4, 5, 6, 7 is here. So 20. 1, 2, 3, 4, 5, 6. No, I made a mistake. 2, 3, 4, 5, 6, 7. Is here 7. About here. We can just estimate this is one box, 24, 28, so 26. So gain margin is 26 dB. Positive, not negative. But this is a stable system. Remember, a stable system, we give positive gain margin. So here, gain margin 26 dB. Then phase margin. Phase margin is obtained by obtaining first the gain crossover frequency. When at 0 dB, we look into the gain. Okay, this is known as this value about 0.8 is known as the gain crossover frequency. Okay, 0.8 So gain crossover frequency is 0.8 radian per second. The phase margin is obtained by taking at 0.8, here 0.8, 0.2, 3, 4, 5, 6, 7, 8, here 0.8, and this is phase margin. Phase margin is between those where the angle, the phase, up to 180 degrees. So what is the value here? Uh, 1, 2, 3, 1, 2, 3, 9, 45, 9. 9, I mean 9, one box is 9 degree. So 9, 4, 99 for 1. This is a so 104 minus degree. Of course, this is not accurate. You can calculate yourself. You can estimate yourself. From my estimation is 1 minus 104 degree. If this is 104, then phase margin is 180 degrees minus 104 is 76 degrees. So it's not 100 plus, 76 degrees. Phase margin. Any question? Phase margin, gain margin and phase margin. Any question? In the exam, it is only 1 mark. 1 mark for phase margin, 1 mark for gain margin. So make sure you can obtain a correct one. Okay, next. Using the dot plot given, find the static error constant and also the steady state error. We want to find steady state error using the dot plot. Okay, if we look into previous slide, this is the one that we discussed about dot plot. Okay, dot plot and steady state error. If we have, you remember, this is for type 0, type 1, type 2. We can know what type of the system by looking into, of course, by looking into the transfer function, and also based on the what we call the magnitude at the lower frequency. From here, you can see that the system is system type 1. Why type 1? Because here is S. We can put S outside, S to the power of 1. So system type 1. And system type 1 will start with a magnitude with a slope of minus 20 dB per decade. You can see, you can prove this. You can see this is 1 decade. and it should be reducing by 20 dB. You can see from here to here 20 dB. More, about 1 decade is 20 dB. You can see? So it is minus 20 dB per decade. And it is a type 1 system. If we do not know the transfer function, we can also estimate the type by looking into the magnitude at the earlier frequency, low frequency. Okay, type 1, how can we get the error? Type 1 will be like this. This is minus 20 dB per decade. What we will do, we will make the line continue until 0 dB. And this value is called KV, static error constant. So I will make this one. It seems that it's already a straight line. I will make straight line here. I use red. Straight line here. Until 0 dB. It's already at here. Okay, it is here. This is from this is actually already a straight line until 0 dB. In fact, after 0 dB. But if we have like this, then we have to make a dotted line to reach 0 dB. So here we get about 0.8, the same here. This is equal KV. 0.8 is KV. And error is 1 over KV. 1 over 0.8, which is 1.2. That is the error obtained from the dot plot. Any question?
No, Doctor.
We will stop here. We will continue with this example in the next lecture. Before that, I want you to try number 3 until number 6, again as a homework. Okay. Number 3, number 4, and 5 is using gain adjustment. Number 3 is just an explanation. Number 4 and 5 is gain adjustment. Please try this at home. We will discuss in the next class solving this example. You need to print the one that I give to you, the dot plot that I give to you, so that you can do on the paper, on the graph paper, semi-log graph paper. Right? Thank you very much. If you have question, any question?